Hello YouTube, welcome to this video, and today we are going to be taking a look at an elastic collision problem and solving it using a Python animation. Stick around till the end of this video if you want to take a look at a more traditional pen and paper based solution. Well, we have a problem of three elastic bodies colliding on a single axis. So we have three perfectly elastic smooth spheres, A, B, and C, all of the same diameter, and having masses 2 kg, 1 kg, and 2 kg respectively. And they're all placed on a smooth, frictionless surface in that very order. And we have A projected towards B with a speed of 27 meters a second. So we'll have A hitting B, then B will hit C, right? It only makes sense. And maybe B will hit A again, but we'll find that out in our Python animation. So stick around till then. And we are tasked with finding out the final velocities of A, B, and C after all impacts are accounted for. To be able to accomplish our animation, we'll have to use this really important equation, and it's the final velocity of an object in a perfectly elastic collision. And you can basically get this equation from the conservation of momentum and conservation of kinetic energy, as those are the two quantities that are conserved in a perfectly elastic collision. Well, so we understand the problem now. We got to find the final velocities after all impacts of all three objects. You know what? Let's jump right into the coding. So here I have opened a PyCharm project, and first things first, we'll have to install matplotlib. So you can go into PyCharm settings, go into Python interpreter, click the plus sign, search up matplotlib, install package, close, okay. We'll do it in the background down here. If you're on the terminal, pip install is the way to go. But anyway, we can start coding now. So create a new Python file. I'll call it main.py. I right-clicked on Python project 3 up here, clicked on new, and yeah, I got this dialog box. There we go. So we have our main.py file created. We can get coding now. First things first, import matplotlib.pyplot as plt for conciseness from matplotlib.animations. Where is it? Animation, import func animation. Now we can define our initial conditions, masses, velocities, etc. 212 velocities and VC. That's going to be 2700. Now, please note, we don't have to be concerned about vector components here. Why? Because we're operating in one dimension. We're operating in the vector space R1, nothing higher. Not even R2, not R3. So we don't have to be concerned about XYZ components, or for that matter, fourth or fifth dimensional components if you're in the movie Interstellar. But yeah, that's only for that. But anyway, coming back to the coding, we will set the positions to -202. You'll see that's arbitrary. The diameter will be 1. And you see why I did that? Because it's going to be evenly spaced out. That's why. Now we can set the time increment to be 0.01. And we'll have to multiply that by a factor called the playback speed. Reason I'm adding that in there, we don't have to, but you'll see the animation will be way too fast for us to easily visualize. So I'm going to add that dynamic aspect to the program there, and we'll set it to 1 for the time being. We'll change it. You'll see it'll be helpful changing it. Now we can work on the elastic collisions function, and that's going to be taken in inputs of M1, M2, V1, V2. And why do I need this? Well, it's to update the velocities. As you'll see, V1 new is equal to M1 minus M2 times v1 plus 2 times m2 times v2 divided by m1 plus m2. We can copy paste the exact same thing, but for v2 we just have to change the subscripts. I'll write v2 new, and then we'll change that, swap them around, change that, keep the denominator the same. Alright, we'll have to return v1 new and v2 new as well. Great. Now we'll initialize the velocities into an array. You'll see why we're going to be doing this very shortly. V and VC. And now, this is the non-physics part is about to come. I'm just going to dash through this really quickly. And there we are. So this first part just sets up the plot. You can play around with these values if you want. You can change a x limit and y limit. The reason we have a y limit, although we don't really have a y-axis, it's because to fit this text box here, that's going to display the velocities as the animation rolls. I can make the font size 12, why not? And then the spheres. We are defining it xy position, right? So we're having the positions I, that's going to be x, and then 0 because we don't have a y-axis. I mean, we could swap it around. We could have all the animations on the y, keep x as 0, but that's more conventional. And as you see, for I in range 3, that's because we have 3 spheres. Simple as that. Really simple. But this is kind of standard for many matplotlib animations. Now we have to make the most important function here, and that's going to be called def update. We're going to be updating frame by frame. So we're going to make global positions and velocities as we're going to access those arrays over here. And we want to update the position first of all. Okay, update positions. And so positions are going to be equal to positions I plus velocities I times the tiny time increment for I in range 3. So for each of the spheres, each of the 3 spheres, we're going to be doing some basic kinematics. Final position is going to be equal to initial position plus velocity times the change in time. Right? That's just basic kinematics that we'll have to apply to update the animation. That's easy, right? Now we'll have to check for collision. Check for a collision between A and B, and we'll have to do the same for between B and C. And if we want to be super redundant, yes, we can check for a collision between A and C, but we know that's never going to happen. I mean, if you're making your program super dynamic and you can, add like 50 other collisions that happen in here, yes, you can add the A and C, but we want to make this program efficient. No need to add it for our purpose here. So how do we check for a collision? Well, if the distance between A and B is less than or equal to the diameter, right? Then there's a collision. Same thing for any 2 spheres. So if the distance, so absolute value, that allows us to have distance, positions 1 minus position 0, as less than or equal to the diameter. Oops, misspelled that. Diameter. Then we can update the velocities based on the fact that a collision occurred. So therefore we'll have to invoke the elastic collision function to update the velocity. So we want to input MA, MB, velocities 0. Oops, velocities 0 and velocities 1. We can do the same thing for B and C. All we have to do is just change the indexes. So that would become 2. That would become 1. That would become 1. That would become 2. That would become B. That would become C. That would become 1. That would become 2. Great. We can now move on. And we can update the sphere positions, right? Because we've checked for a collision. And we know it's happened or not happened, so therefore we can update the positions of the spheres. So for I, sphere enumerate, where is that? Enumerate spheres. Great. We can sphere.setCenter to double bracket positions I, 0. Why do we not change the y-axis? Well, we're not using it once again. So hence why we keep that to 0 and we change the x to positions I. All right. We can now update the velocity text. So I shall add that down here. That's kind of like our the little text box that has the live velocities of the collision. It's kind of like the telemetry. If you've ever watched like rocket launches live, they have always a telemetry which shows you the live velocity of the rocket. Same thing here, but for these basic spheres. Great. Well, to explain what it does, it just uses an f string, a Python f string, and rounds to 2 decimal places. That's what the 2f means. The velocities in meters a second. That's all it does, and displays it to the user. Last but not least, return spheres with the plural, plus velocity text. And that's it. We can now create the animation. And that would be animation is equal to func animation. We would input fig update frames is equal to 1,000. And interval equals 10. Important part, divided by the playback speed. And then BLIT, this is just a Boolean variable there, set it to true. And finally plt.show, and this should work. So if I press play, look at that, it works. Great, but how come the velocities did not change? Well, that's because we got to change the playback speed. All right, let's make the playback speed to 10%. We shall play. Look at that, 27 meters a second. It hits ball B, updated, right? They collided, B and C. Now look, B and A collide again. And that is it. These are the correct answers, as in, well, the answer key. And now it's time to show a regular paper-based solution to this. And that's right over here. So basically, I did not have the equation that I put in the LaTeX document, the PDF, right on hand. So I just did a manual system of equations, right? And as you see, A collides with B. And I did a system of equations, and you get 36 and 9 meters a second. Then you use that value. You use the speed of B after the first collision, 36, and use it inside the second system of equations between B and C. And then you kind of got to visualize it in your head and know that A will collide with B for the second time, and use the updated value of B and the updated value of A. And you will get the final answer of 16 minus 5 for A and B. And then for C, you just have to write down that that's going to be 24. And well, that is it. Thank you for watching this video. I hope you enjoyed it and have a wonderful day.